Hey everyone, and welcome to The Explainer. I am super thrilled you're tuning in today because we're going to decode something pretty mind-blowing: the invisible, absolute, high-speed journey of data from the moment it's created all the way to your screen. We live in this world that's just overflowing with instant information, right? But honestly, most of us rarely stop to think about the literal gymnastics, physical and logical, happening behind the scenes to make it all work. So today, we are mastering communication systems and networking. But before we jump straight into the theory, let's anchor this to reality. Just ask yourself right now, how is this very explainer reaching your personal device? I mean, I didn't perform magic. I spoke into a camera, which digitized my voice and my image. That data traveled from my computer, pushed through local routers, zoomed out across citywide fiber optics into some massive server, and then navigated all the way back through a complete maze of a network directly to the screen right in front of you. So here is our roadmap for today. 1. Foundations of data communication. 2. Bandwidth, calculating data speed. 3. Transmission methods and packaging. 4. Data flow and distribution. And 5. Cables, physical media. All right, let's jump right in. Section 1. Foundations of data communication. Okay, so there are 5 core elements required for absolutely any data communication to happen. Let's use the process of uploading a video as our example here. First up, you have the source. That's the actual video file sitting on my computer. Second is the sender, my computer itself, which is preparing that data. Third, the medium. These are the actual internet cables and Wi-Fi waves the data is traveling through. Fourth, the receiver, the giant servers hosting the platform. And finally, the 5th element, the protocol. Protocols are basically the strict sets of rules both computers must agree on, like HTTP or TCP, so they can actually understand each other. And this perfectly illustrates a major technical hurdle we have to overcome. See, computers speak in digital binary. They deal in zeros and ones with very sharp, square edges. But the physical mediums out there, like copper wires or just the air around us, they carry analog waves. They literally can't handle those sharp digital edges directly. So this is exactly where your modem comes in. It performs modulation, converting that digital data into smooth analog waves for the journey, and then demodulation at the other end, translating those waves right back into sharp digital binary for the receiving computer. Moving right along to Section 2, bandwidth, calculating data speed. Okay, so understanding bandwidth is absolutely crucial. Bandwidth is simply your data transmission rate, and it's universally measured in bits per second, or BPS. Now, I really want to clarify a fundamental metric here because it trips up a lot of people on exams. Notice that lowercase b. When your internet provider sells you a 10 Mbps connection, that is megabits, not megabytes. Because there are 8 bits in a single byte, a 10 megabit connection is actually only transferring data at about 1.25 megabytes per second. Always watch out for that lowercase b. It's kind of wild to see how data speed literally categorizes the evolution of our networks. I mean, we started with narrowband, running at a crawling 45 to 300 bits per second. Basically, think of old telegraphs. Then came voiceband, which pushed things up to 9.6 kilobits per second, which became the standard for your landline telephones. And finally, we hit broadband, starting at 1 megabit per second and scaling massively upwards from there. That's what's powering your home Wi-Fi and all your modern video streaming today. All right, let's keep following our data's journey in Section 3, transmission methods and packaging. So, how do we physically send these bits? We basically have 2 options, parallel and serial. Parallel transmission is kind of like a multi-lane highway. You send an entire 8-bit byte at the exact same time over 8 separate wires. It's incredibly fast, obviously, but running multiple wires over long distances is incredibly expensive, and it causes a ton of electrical interference. That is exactly why long-distance communication relies on serial transmission. It's a single file line. You just send one bit after another over a single wire. Sure, it's a bit slower, but it's super reliable, and it's absolutely perfect for spanning across cities or even oceans. Now, within that single file serial transmission, we actually have different ways to package the bits. The first one is asynchronous transmission. Imagine typing on a keyboard, right? You press a key, the data goes instantly, but then you might pause for 10 seconds before pressing the next key. Because that timing is totally predictable, the computer literally has to wrap every single character in extra start and stop bits. That way, the receiver knows exactly where a specific piece of data begins and ends, which builds into a much more efficient method called synchronous transmission. So instead of sending one tiny character at a time, the sender gathers a massive chunk of data, let's say 80 to 132 bytes, keeps it in its memory, packages it into a single solid block or frame, and then sends it all at once at fixed intervals. Think of it like a delivery truck taking a huge load of packages across town in one single trip, rather than a courier running back and forth for every individual envelope. And this brings us to some pretty striking math. If you're using asynchronous transmission, adding those start and stop bits to every single character means you are wasting a lot of space. It actually ends up being only about 72% efficient. But synchronous transmission? Because you're grouping massive blocks of data and only using a single header and trailer for the whole block, your efficiency skyrockets to 95.23%. That is exactly why synchronous block packaging is mathematically superior when you're transferring large files. Okay, let's look at the rules of the road in Section 4, Data Flow and Distribution. When devices connect, they have to agree on how traffic is going to flow. Simplex mode is strictly a one-way street. Data only flows from sender to receiver. Think of a television broadcast. Half duplex is a two-way street, but here's the catch. Only one lane is open at a time. It's exactly like using walkie-talkies, where you have to say over before the other person can start speaking. Finally, we have full duplex. This allows two-way simultaneous communication, just like a standard phone call or a modern video chat where both people can talk and listen at the exact same time. And when a sender wants to reach multiple receivers, they've got choices there too. Broadcast is basically like picking up a loud megaphone. It blasts the data out to absolutely every single user on a network simultaneously. Multicast, on the other hand, is highly targeted. It selectively distributes data only to a specific, authorized group of users on that network and completely ignores everyone else. Finally, let's look at the actual roads our data drives on in Section 5, Cables, Physical Media. So the most common cable you're going to see plugged into an office computer is the twisted pair cable. But here's the thing. Those copper wires aren't twisted together just to look nice. Whenever electricity flows through a wire, it generates a magnetic field that can actually corrupt the data in the wire right next to it, a really annoying problem called crosstalk. But by physically twisting the pairs of wires together, physics takes over. The opposing magnetic fields literally cancel each other out, which protects our precious data from electromagnetic interference. Now, if you need to go over longer distances or you're in an environment with a ton of electrical noise, we use coaxial cable. It's that thick wire you probably use for your TV dish. Coaxial cables use a solid central copper core to carry the voltage signal, but then they wrap it in a thick plastic insulator and heavily armor it with a woven metallic shield. That heavy shielding acts like a literal fortress, blocking all that outside electrical noise from ever reaching the data inside. But to get to the unbelievable speeds we expect from the modern internet, we actually had to leave electrical voltage behind entirely. Enter the ultimate upgrade, fiber optic cables. Instead of electricity, fiber optics transmit data as rapid, microscopic pulses of infrared light. By utilizing this really cool physics principle called total internal reflection, the light bounces perfectly down the inside of the cable without ever escaping, meaning our data is moving, quite literally, at the speed of light. If you peel back the anatomy of a fiber optic cable layer by layer, it is just an absolute marvel of engineering. Right at the very center is the microscopic glass core, where the light travels. Wrapping that is the cladding. It's a slightly different type of glass that acts like a perfect mirror, forcing the light to continuously bounce back into the core. Then, all of that is surrounded by a protective coating, a rigid strength member so the super delicate glass doesn't snap if it gets bent, and finally, a rugged outer jacket. So when we summarize the evolution of our physical media, the contrast is pretty stark. Copper cables rely on electrical voltage, which naturally makes them susceptible to magnetic noise, and that limits both their speed and their distance. Fiber optic cables, by utilizing pure light, are completely immune to electrical noise. They can transmit mind-boggling amounts of data all the way across oceans in a fraction of a second. It's basically optical perfection. Well, we have unpacked an incredible journey today, from basic bits and baud rates to blocks of literal light racing under the ocean to reach your screen. But as wireless networks and satellite constellations continue to blink at the globe, it leaves us with a really provocative thought. As technology continues to evolve beyond our current horizons, will the future of communication eventually bypass these massive networks of physical cables entirely? Thank you so much for joining me on this explainer. Keep asking questions, and I'll catch you next time.